Hi all, welcome to the new session. In our previous sessions, we learned the important concepts of dynamics of rigid bodies. We discussed what is moment of inertia. We discussed the moment of inertia of different shapes. So, in this session, we are going to discuss the moment of inertia of a mechanical device, which is nothing but the flywheel. So, in this portion, we need to derive the equation of moment of inertia of the flywheel. Also, we need to perform the experiment. We need to discuss how to perform an experiment if you want to calculate the moment of inertia of the flywheel. So, let us move to the topic. So, this is the content which I would like to include in this session. First, we will give you a brief introduction on flywheel. Then, we will discuss the theory to determine the moment of inertia of the flywheel. Then, we will demonstrate the experiment virtually to determine the moment of inertia of a flywheel. So, what is a flywheel? It is a large heavy wheel with a cylindrical axle which is passing through a center of mass, so that it is freely rotate about the axis of rotation. So, you can see there is a large heavy wheel with a central axis passing through the center, so that it can rotate. The most important property of the flywheel is the center of mass of the system lies at the axis of rotation, so that the flywheel can remain at rest at any position. Also, you can see there are rotational parts. So, we need to expect the frictional force. So, we are just using ball bearings to minimize the friction. And the most important quality of the flywheel is its mass is mostly concentrated at its rim. You just focus on its shape. You can see the mass is concentrated at its rim. Can you say what is the reason for this? Because of this, you know, since the mass is concentrated at a distance from the axis of rotation, you now know its moment of inertia will be very high. So, the moment of inertia of the flywheel is very high, since the most of the mass is concentrated at its rim. So, what happens when the moment of inertia is very large? When the moment of inertia is very large, it gives the motion of the flywheel a steady and smooth motion. You know, in the translatory motion, when the mass is very large, it won't affect the external fluctuations caused by the external force. Similarly, if the moment of inertia is very large, the velocity or the speed remains as such, even though the torque is different. So, in the case of the flywheel, the moment of inertia is very large and it makes the motion of the flywheel smoother and steadier. So, this is one of the important property of the flywheel. Okay. So, next we need to see, in many situations in our everyday life we can see the importance of flywheel. So, you can see this is a large heavy wheel and the ball bearings are here. So, in this picture you can see the flywheel is used in rotating parts of large machines, because it helps to supply the continuous supply to the engines, even though there is an intermittent power supply. So, it is also used in swing machines. You can see two flywheels are used, one big and one small, and also in the petrol engine. In our bikes, cars, the flywheels are used in after the crankshaft arrangement. So, the flywheel will give or will supply the continuous power to the wheel, even though there is a discontinuous supply from the cylinder during the combustion stroke. So, in this way the flywheels are used in many situations in our everyday life. So, there is the importance of flywheel to discuss in this syllabus. So, this is an experimental setup to determine the moment of inertia of the flywheel. So, now we are just going to derive what is the equation of moment of inertia of a flywheel, or how we can calculate the moment of inertia of flywheel. To find the moment of inertia of a flywheel, we need to We need to place the flywheel at a particular height. You can see a flywheel here, there is a cord, there is a weight hanger, there is a meter scale. So, for determining the moment of inertia of a flywheel, for starting the experiment, you need to place the flywheel at a certain height above the ground. Okay. So, you need to take a cord or a small pin. A pin is attached at the axle. You need to take a cord So, one end of the cord is slipped onto the peg, a weight hanger is attached at the other end. So, before starting the experiment, you should be more careful that the cord or the length of the cord should be so adjusted that the weight hanger just touches the ground. Here you can see some 8 centimeter is wrong. You just place the weight hanger in such a way that it just touches the ground. If suppose this is the floor, you need to place the weight hanger in this position. So, in this way you need to adjust the length of the cord. Okay. So, this is the initial arrangement. So, you can see a marking on the flywheel to count the number of rotation. So, for that, for starting the experiment, we just place the flywheel at a certain height. We took a cord and one end of the cord is slipped onto the peg and a weight hanger is attached at the other end, and the length of the cord is so adjusted that it just touches the ground. Now, just release the flywheel, do not push it, just release the flywheel. So, you will see what, and before that we need to rotate the flywheel backwards. Okay. We need to rotate the flywheel backwards so that the cord will wound over the axle. You can see if you rotate the flywheel backwards, the cord will wound over the axle without overlapping. That is also very important. You need to see that the cord is wound evenly over the axle. So, for that you just give a definite number of rotation backwards. Suppose you can see here 4 rotations are there. So, 4 times it wound over the axle, so that the weight hanger raised to a height h. Let it be a h. So, at the initial position the weight hanger is just touches the ground, is at a position when it just touches the ground. So, when the flywheel rotates backward, the weight hanger raised to a height h, so that it gains some potential energy, you know. So, when it raises to a height h, it gains some potential energy, you know the expression, it is nothing but mgh. So, this is the arrangement. So, at this position the weight hanger is at a height h above the ground. Now, you need to release the flywheel. So, what will happen? If you release the flywheel, the mass m falls under gravity. If you release the flywheel, the mass m falls under gravity, so that the cord unwound. So, the cord begins to unwound and the flywheel rotates. So, when the mass is falling under the gravity, the potential energy gained by the mass, or the mass lost its potential energy, and the flywheel gains some kinetic energy. Okay? When the mass gets detached from the axle, the flywheel rotates and it begins to unwound, so that the potential energy of mass is decreasing and the flywheel is getting some kinetic energy. When the cord is completely unwound over the axle, the load strikes the ground and the cord slips off the peg. So, this is what happens. When it completely unwounds, it just released and it strikes the ground and the cord slips off the peg. Since the flywheel is gaining some kinetic energy because of this falling mass, it will continue to rotate before it comes to rest because of the frictional force at the ball bearings. So, the flywheel will continue to rotate and comes to rest after some definite number of rotation because of the frictional force. So, in short, the potential energy lost by the mass is partly converted to increase in kinetic energy of the flywheel and the mass. So, both the flywheel and the mass will get some kinetic energy, and a partly is converted to do some work against the friction between the axle and ball bearings. Okay. So, this is what happens. As per the law of conservation of energy, the potential energy lost by the mass is partly converted into kinetic energy of the flywheel, kinetic energy of the falling mass, and partly to do some work against the friction. So, this is the experiment. Okay. You please remember, at the initial point we are just placing the flywheel at a definite height and we are just taking a cord. The cord is one end is slipped onto the peg and the weight hanger is attached to the other end, and the care should be taken that it just touches the ground. Now, the cord should be adjusted that it just touches the ground and give some definite number of turns backwards, then release the flywheel. The cord or the load or the mass will strike the ground. So, at this point, when the cord or the mass detached from the axle, the flywheel will make a rotation, for example, N rotation, capital N rotation for a particular time t before it comes to rest. Okay? Or let the t be the time taken by the flywheel to complete capital N rotation before it comes to rest, when the cord detached from the axle. So, at first you are giving some number of turns, it is small n. This n represents, it is the number of rotation made by the flywheel after the cord detached from the axle. So, that is very important in a time t. So, as per the law of conservation of energy, we can write decrease in potential energy of the mass equal to increase in kinetic energy of the flywheel and the mass plus work done against the friction. Mathematically, we can write the potential energy gained by the mass, if it rises to a height h above the ground, it is mg8. It is converted to first one, what? Decrease in potential energy of the flywheel. So, rotational kinetic energy, sorry, increase in kinetic energy of the flywheel, it is rotational kinetic energy half I omega square plus increase in kinetic energy of the mass. It is in the translatory motion. When the mass falls down under the gravity, it will have some kinetic energy and it is given by half mv square, half mv square. And partly to do some work against the friction, we are just assuming that let small w be the work done against the friction per rotation of the flywheel. Let small w be the work done against the friction per rotation or in a single rotation of the flywheel. So, if it makes small n rotation, so in the initial stage it is making small n rotation, then the work done to overcome n rotation is given by, it is nw. Okay. So, this is the equation. The potential energy lost by the mass is partly converted to kinetic energy of the flywheel, kinetic energy of the falling mass and work to overcome the frictional force. Here n stands for this n, because in the initial stage the number of rotation which is going to make by the flywheel is n, because it needs to unwound completely, right. So, it has to make small n rotation. For that it has to do nw work to overcome the frictional force. Here you know I is the moment of inertia of the flywheel, omega be the angular velocity of the flywheel and v is the velocity of the falling mass, w is the work done against the friction per rotation. So, now what happens? The mass gets detached from the axle and the flywheel makes capital N rotations. So, for making capital N rotation, the rotational kinetic energy of the flywheel, it is half I omega square. It must be equal to the work done to overcome the frictional force for this capital N rotation. It is given by nw. So, half I omega square equal to nw. This is the second case when the mass gets detached from the axle. From this we can calculate what is w, work done against the friction per rotation. Half I omega square equal to nw, or w equal to what? I omega square by 2n. I omega square by 2n. So that we got what is the expression of the work done against the friction per rotation. Now substitute this W in this equation 1. Substitute this value of W in equation 1. So it is mgh equal to half I omega square plus half m v square plus n into I omega square by 2n. N into I omega square by 2n. So you can take 2 LCM. So 2 mgh equal to I omega square plus m v square plus it is I 2n I omega square by 2n. 2n I omega square by 2n. From here just take 2 mgh minus m v square and take what? 2 to cancel out, I omega square outside, and it will give you I omega square into, so here small n is also here, so I omega square into 1 plus small n by capital N. 1 plus small n by capital N. So 2 mgh minus mv square equal to I omega square into 1 plus small n by capital N. Here you know what is V? V equal to R omega. V equal to R omega. Just substitute V equal to R omega in this equation. So that we will get 2 mgh minus m into R square omega square minus m into R square omega square equal to I omega square into 1 plus small n by capital N. Here we need to substitute omega. You please understand, when the flywheel rotates, it rotates with an angular velocity omega, but when it stops or it after making n rotation, it comes to rest, so that the angular velocity is 0. So the average angular velocity is nothing but it is omega plus 0 by 2, right, which is omega by 2, omega by 2. So omega by 2 is the average angular velocity of the flywheel, which is equal to what? 2 pi, it is equal to what? 2 pi f. F is the frequency. Since it makes capital N rotation in a time during the time small t, so it is 2 pi n by t, n by t for the frequency. So omega by 2 equal to 2 pi n by t, or what is omega? Omega equal to 4 pi n by t. So this is an important concept which is there in the derivation. You have to take the average angular velocity of the flywheel, which is given by omega by 2, and just equate this with 2 pi f, which is 2 pi n by t, since it makes capital N rotation before it comes to rest during the time t. From that you will get omega, which is omega equal to 4 pi n by t. Just substitute that omega here, so that you will get 2 mgh minus m r square 16 pi square n square by t square equal to I into 16 pi square n square by t square into 1 plus small n by capital into 1 plus small n by capital N. At this point, just multiply throughout the equation by t square by 2 and write the expression. So at this point, multiply throughout by t square by 2 and just write the final expression. So that is 2 mgh into t square by 2 mr square into 16, this one into t square by 2, this one into t square by 2. So that you will get the final expression as I equal to just check whether you are getting the final expression after multiplying t square by 2. It is equal to mgh t square minus mr square 8 pi square n square divided by, so multiply with throughout by t square by 2 and rearrange the equation for I. So that you will get I equal to mgh t square minus mr square 8 pi square n square by 8 pi square n square into 1 plus small n by capital N into 1 plus small n by capital N. So take the LCM here, n into n plus n, just send the n to the numerator, so that you will get nm by n plus n. Okay. So this n plus n is here, n to the numerator, so nm by n plus n. So what's remaining? gh t square, gh t square by 8 pi square n square by mr square, 8 pi square n square, 8 pi square n square, cancel it out. So that the remaining, it is m we are taking as common, so only r square there. So gh t square by 8 pi square n square. We know what is omega. Here omega equal to 4 pi n by t. So what is omega square? 16 pi square n square by t square. So here we have 8 pi square n square by t square. So multiply 2 on both sides, in the numerator and the denominator, so that it will become 16 pi square n square by t square, which is nothing but omega square. So the final expression will get I equal to nm by n plus n into 2 into gh by omega square nm by n plus n into 2 gh by omega square minus r square. So this is the final expression to find out the moment of inertia of the flywheel. Here n is the number of rotation makes by the flywheel when the core detached from the axle, m is the mass attached, small n is the initial rotation makes by the flywheel, g acceleration due to gravity, h is the height which is raised above the ground, omega angular velocity, and small r is the radius of the axle. Okay. So in this way we can calculate the moment of inertia of the flywheel. Please go through all the derivations very carefully and write to yourself and just derive the expression completely. So with this I am just concluding this session. In the next session we will see how to do the experiment to find out the moment of inertia of the flywheel. Thank you. Bye for now.